Why should a machine learning program learn how to play a game? Researchers are interested in improving how AI systems learn. And games provide both challenges as well as a constrained environment that's easy to control. This week we'll see how computers that play games have evolved and how the latest breakthroughs show promise for more than just games. In some ways, making a computer program that can play a game as well as or better than a human is kind of like the Turing test ideal. Researchers are fascinated by human intelligence, and many of them have tried to develop a machine or software that can go head-to-head with a human. You remember the Turing test is passed if the computer fools a human interrogator into thinking that the computer is a human being. With games, the goal is not to fool anyone, but to actually be as good as or better than a very good human player of the game. Like the Turing test, this could be seen as a demonstration that the machine has intelligence. Having an agent learn how to play an old-school video game is a nice shortcut for reinforcement learning because a platform with all the games built in already exists. So the researchers don't need to build and program the game and its rules. All they need to program is their agent and how it should learn. These Atari games were really simple, so they provide a good way to start developing a system that learns. The agent has actions available to it that are equivalent to joystick motions and button presses on a game controller. The game in real time is 60 frames a second, but the simulator can run at up to 6,000 frames per second. So an agent can run through a lot of learning episodes very, very fast. Now, we are not going to get into the weeds about how Q-learning works in a convolutional neural network. Just bear in mind that it was combining these two techniques, Q-learning and ConvNets, that gave DeepMind researchers an edge. They called the approach Deep Q Learning, and they called the system a Deep Q Network, or DQN. DeepMind is the company that created AlphaGo, and later we'll learn more about how they've gone beyond games with a protein folding algorithm that's been hailed as revolutionary. You'll see the founder of DeepMind, Demis Hassabis, throughout the film about AlphaGo. So in case you've been wondering, why do all these engineers and programmers and neuroscientists spend time on games, on figuring out how to get computer programs to learn to play games? The games are not an end in themselves. As I already said, games provide a good way to start developing a system that learns. Now, I do want to reiterate one crucial point about reinforcement learning, and that is the agent chooses its next move based only on the current state of the environment. As soon as an action is done, there is a new state. The actions available to the agent depend on the current state. As the agent learns, the value of each action in a particular state is adjusted. Each move creates a brand new state. The next move or action for one agent is evaluated based on the current state. So here's the difference between using a Q table for reinforcement learning and using a neural network. At each step, the neural network looks back at a small number of previous states. It can then adjust the values for the actions taken in those states based on the success or lack of it in the current state. Obviously, when the current state got a reward, this adjustment is really important. And just for fun, here is DeepMind's own representation of its network that learned to play the Atari games. Now, that's as far into the weeds as we're going to go for the way that DeepMind's program works, the program that plays the Atari games. And of course, there are equations and hyperparameters that have been tweaked to perfection by the human programmers to make this system work well. DeepMind used the program to learn to play 49 different Atari video games. After learning was complete on each game, the program was better than a human expert player on more than half of the 49 games. It was more than 4 times better than an expert human player on 8 of the 49 games. And in one game, Breakout, the program's average score was 10 times better than the average for the human expert. In case you were wondering, the average score for the human expert was obtained under controlled conditions. Now, there is a reason why this story about reinforcement learning is so much about DeepMind, and that has a lot to do with AlphaGo, their Go-playing program, which came after the Google acquisition, which came after the Atari games. Before we talk about that, we need to travel back to the time around the Dartmouth AI workshop in the 50s and something that happened with the game of checkers. An IBM engineer named Arthur Samuel got the idea to do this, to program a computer to play checkers on its own using IBM's very first commercial computer. He set up the program to step through what's called a game tree. This diagram represents a game tree for one move. Or more accurately, using terms you already know, it's the tree for one state in one game of checkers. So you're going to look at all the possible actions in that state. So whoever's turn it is, whichever player, there are several possible moves, right? Those moves are the actions. Now, a complete tree would take the computer program all the way down through all possible results from each action that is available in this state. And the lowest level would be when somebody wins and somebody loses. But the game of checkers had too many possible moves, has too many possible moves and states for a computer at that time to look at the complete tree. Even for a simple game like tic-tac-toe, the game tree can go pretty deep. Suffice to say that with certain algorithms, the game-playing program can travel a short part of the game tree and make a pretty good prediction of the best move. In addition to the game tree, Arthur Samuel's checkers program incorporated 2 other important aspects of letting a program learn to play a game on its own. One is the evaluation function, which is a system for evaluating board positions, or states, at the end of a branch in a partial game tree. The other is having the computer program play itself. This leads not only to faster results, because the computer can make moves much faster than a human can type, but also the program can get better at the game than the person who programmed it by having 2 programs play each other. The evaluation function is where the learning happens. This function tells the program which board is the best outcome, looking 4 or 5 steps down the game tree. It evaluates each possible board position at that level of the tree, using comparisons between the two sides, red and black for checkers, right? Comparing the number of pieces left on the board for each player and the number of pieces that are kings for each player, and so on. Some math is done, and then there is a numeric rating for each board position. The best move right now is the move that leads to the board with the highest rating. So that's the move the program will choose to play. The checkers program learned which things were important on the board at which stage of the game. Some things are more important at the beginning, other things are more important nearer to the end. An important thing to bear in mind is that checkers is a pretty simple game. Chess is more complex for one reason, because it has 6 different kinds of pieces, and they each move differently from one another. In checkers, all the pieces move the same way, and they're equal to one another. In chess, the goal is to trap the king so that the king cannot escape. This takes some complex moves, right? Whereas in checkers, the goal is simpler. It's just capture all your opponent's pieces, or make it so that your opponent can't make any more moves. So I say this is important to bear in mind, that how simple checkers is, because it was a much bigger deal to program a computer to play chess well than it was to program a computer to play checkers. And then Go is much more difficult than chess. All of this serves to illustrate how machine learning has advanced through playing games. There's actually a long history of people imagining a machine that could play chess, from even before when computers existed. And there are ideas about human intelligence tied up with this too. Mitchell points out that chess has long been considered an intellectual game. So if a computer could learn to play it well, then would that mean the computer was intelligent? For a long time, people thought that answer was yes. Well, we've been around that loop-de-loop before, haven't we? Just because a computer can do things that indicate intelligence does not mean that that computer has intelligence. And yet, the hype surrounding an IBM computer's defeat of the world chess champion, Garry Kasparov, in 1997 was epic. People didn't talk so much about the fact that Deep Blue could not do anything other than play chess. More important than that, Deep Blue did not use machine learning in any significant way. It was a specialized machine. It even had specialized hardware designed specifically to run faster and deeper into the game tree. Another point about the Deep Blue victory is that it followed a disappointing defeat in February 1996, just a little more than 1 year earlier. In that earlier match, the same world champion, Kasparov, beat the computer 4-2. Now, note, 2 of those games were tied, but still, it was a better score for Kasparov. IBM spent the time in between the first match and the second analyzing the games in the first match, studying Deep Blue's mistakes, and retooling to come forward in May 1997 with a better chess-playing system. So since Deep Blue didn't have any machine learning, the program could not improve by playing itself. Because when you have 2 programs play each other, the point is so that each of those 2 programs can become stronger. And then you have sort of generations of the program play each other and they get stronger, and then they play each other and they get stronger still. Both Arthur Samuel's checkers program and DeepMind's AlphaGo played against themselves and that was responsible for how they improved by having one copy of the program play against another copy of the program. Deep Blue's own team said Deep Blue wasn't AI at all. The combination of explicit rule-based programming and deep tree lookups meant that Deep Blue wasn't doing artificial intelligence at all. Or was it? Earlier in this course, we learned that good old-fashioned AI, or GoFi, was based on rules and logic, and even decision trees, which are not very different from game trees. This is worth thinking about. If we went back and looked at the things that were called AI before neural networks, before machine learning, would we still want to call them AI today? Now, it's time to talk about AlphaGo and what it means. Since you have watched the documentary about AlphaGo and its famous victory against the Go champion Lee Sedol, we don't need to spend time reviewing that. But it might help you to understand a little bit about how Go is different from chess and checkers. So, the Go board begins empty at the beginning of the game. There are 361 intersections. You play your piece on the intersection. The piece is called a stone. So one player plays a stone, the other player plays a stone. One player is black, one player is white. The players take turns, the same as in chess and checkers. Stones can be captured, but that is not the point of the game. Stones never move. You either place it on the board or you take it off the board because it was captured, but once it's on the board, other than being captured, they never move. The goal of the Go game is to end with more territory than the opponent. Your territory is empty spaces on the board that are surrounded by your own stones, your color. These specific differences between chess and Go mean two important things when it comes to programming a game that plays one or the other. One, you cannot use a game tree for playing Go in the same way that Big Blue did for playing chess. There are just too many possible moves on each turn. Two, no one has been able to develop an evaluation function that works well for Go. This is because the configurations of stones across the whole board are too varied and too numerous from the beginning of the game right through the middle game up to the end game. Too many possibilities, too hard to judge. Counting the difference in the number of pieces, like you do in an evaluation function for chess or for checkers, doesn't tell you anything in Go. So these reasons show us why machine learning was essential for a computer to play Go well. You could not use a brute force approach like Deep Blue used for chess. You could not use brute force to play Go. You would just never win a game. Your program would be bad. It would not succeed. So the work done by the DeepMind team of programmers, engineers, and neuroscientists on the program that learned to play the 49 Atari video games was directly related to their success with AlphaGo. Now, the AlphaGo program, this is the one that beat the Go master named Lee Sedol in 2016. It had two separate neural networks. One was for Q-learning, one was supervised learning that had specialized Go knowledge, and it also used what's called Monte Carlo tree search. Now, I thought about explaining Monte Carlo tree search in this video or a separate video. Then I reread the explanation in the book, and I thought, if you want to understand how it works, I think The book does a good job of explaining it, and I'm not sure if it would make sense for me to repeat that here. But Monte Carlo tree search was very important to the success of that original AlphaGo program. After AlphaGo beat Lee Sedol in 2016, the DeepMind team developed AlphaGo Zero. Now, the difference between AlphaGo Zero and the original AlphaGo was that AlphaGo Zero was trained solely by self-play reinforcement learning. It didn't have human data fed in. It didn't have dictionaries of moves. It didn't have human professional games fed in. It didn't learn from those games that humans had played. It had nothing but the rules of how to play the game. And it trained by playing itself. So it's called Zero because it started from zero. And after it had gone through its many episodes of learning via reinforcement learning, it was able to win 100 games out of 100 playing the older AlphaGo program that had beat Lee Sedol, the Go master. So AlphaGo Zero really was a whole new program. It uses a single neural network instead of two, and it uses a much simplified tree search compared with its ancestor, the original AlphaGo. Then after AlphaGo Zero came AlphaZero. Notice the word go is gone because this is a new generalized program that could learn Go and other two-person strategy games. AlphaZero uses the same convolutional neural network architecture as AlphaGo Zero. So the two zeros use the same kind of architecture. And in fact, AlphaZero uses the same hyperparameters, algorithm settings, and everything from AlphaGo Zero for all the games that it can play, but it doesn't have any game-specific tuning or fine-tuning other than the rules of the game and the environment of the game. So learning with AlphaZero for each game begins with a fresh, unaltered copy of the program, and then the rules of the particular game and the environment, such as the board and the pieces and how the pieces move, that information is added in, but nothing else. So running on very fast computer hardware, AlphaZero was able to master Go to a level where it could beat AlphaGo Zero in 13 days of self-learning. 13 days. Compare that to how long it took AlphaZero to master chess. It took 9 hours of running the reinforcement learning algorithm for AlphaZero to become a chess master. DeepMind also set AlphaZero to learn how to play shogi, which is a Japanese variant of chess. And that, it's harder than chess, it's more complicated than European chess, but it took 12 hours. Not days. The only thing that took days was Go. But this same program, starting from zero, was able to become expert at 3 completely different board games. We started out last week with a simple idea of a robot learning how to kick a ball based on reinforcement learning, based on getting a reward when the ball was kicked, not getting a reward any other time. This week we moved on to see how using reinforcement learning was successful in training an agent to win different video games. Building on that experience, DeepMind developed the groundbreaking AlphaGo program. Its success at winning multiple Go games against a world champion player was something that AI experts had not expected to happen for another 10 to 20 years. DeepMind's next project was to modify AlphaGo, to re-engineer the program so that it could learn to play other intellectually demanding games all on its own. Where will all this lead? The thing to walk away with here is that playing games was never the end goal. It is a means to an end. The potential of reinforcement learning seems pretty huge right now. It doesn't require labeled data. It doesn't require any data at all. In the course of learning, it generates its own data. What remains to be seen is how many domains, how many different domains will reinforcement learning be useful for. Robots is definitely one domain that looks really promising. DeepMind's latest triumph with a neural net they named AlphaFold does not use reinforcement learning. And I just wanted to throw this one in for you so that you don't get confused. AlphaFold is not any kind of direct descendant from AlphaZero. It doesn't play games. It doesn't use reinforcement learning. It uses supervised learning, deep learning, one neural network. It was trained on data, on publicly available data about protein structures, how they look, how they're put together. And what it does, the purpose of AlphaFold, is to accurately predict the shapes of protein structures given a certain set of proteins. What shape will result. And why this matters is it's very important for drug development, among other things, but drug development, cures and treatments in particular, because drugs work by binding to proteins in the body. And the shape of the protein affects whether they bind or not. So, apart from AlphaFold, that little last bit with 2 slides, our lecture this week has been about reinforcement learning, and specifically how reinforcement learning has been used, particularly by DeepMind, now owned by the company that owns Google, Alphabet. How reinforcement learning has been used successfully to do things with programs, particularly playing Go, but also playing other games that really had been thought not only to be impossible, but it had been thought that once this was achieved, you would have general AI or AGI, right? Like AI that had real intelligence. And you can judge for yourself whether any of these programs are in fact intelligent or not.